Good morning and welcome to Monday, April 20th. This is AP Statistics. We're going to start off just by remembering what we have been doing in the past, and if you need to watch that video again, help yourself. But we were talking about chi-square tests of independence. We already covered goodness of fit. Most recently, we had independence testing. Specifically, that occurs when you have one random sample taken from one population, but you break it down based upon multiple variables. For instance, the actual example escapes me, but if I took one sample of all the students from the school and then I broke it down based upon, let's say, underclassmen and upperclassmen and their preference for, flavor of ice cream, doesn't matter. That would be a test of independence to see if there is any kind of association between the class level and their preference for ice cream, or what kind of ice cream they like. What makes it independence testing most specifically, that separates it from what we're about to do, is the number of samples taken from the number of distinct populations. So in the question I just created, we had one sample taken from one population of the high school. That's an independence test to see if there's an association between, in this case, the year in school and the ice cream flavor preference. So the difference here with today's unit is that we're going to cover the last part of chi-square testing, which is called homogeneity, which is like sameness. All right, so we're going to do an example for chi-square test for homogeneity. Okay. The setup is kind of simple. It's going to look similar to independence testing. The approach, the process, very similar. There's distinct differences, though. First distinct difference, homogeneity testing. There are two samples, and they're taken from two different populations. Okay? That's kind of a clear distinction. It doesn't test for an association. The word association is used for the independence tests. It tests for, we'll say, whether or not the populations are distributed equally or distributed the same. I'll say that. Okay. So if I took one random sample of Shelton High School students and another random sample of Los Angeles High School students, and I wanted to see, let's say, their breakdown for freshman, sophomore, junior, senior, all right? What we'd be testing is to see whether or not high school in Shelton and high school in Los Angeles have equal breakdown of grade level students. So would the distributions be about the same? Now, that doesn't mean that everything has to be 25% either. All right? We could have more freshmen than seniors. It's fine. If that just is the same between the two populations of Shelton versus LA, that would be our null statement. So our null is talking about whether the distributions of the two populations are approximately the same, and the alternate would be that they're not. The only additional difference is in the conditions also. Conditions have to be met for both of those samples. With independence testing, we just had one sample, so we only had one set of conditions. But for homogeneity testing, we're taking two distinct samples from two distinct populations. So the conditions have to apply to both. All right, well, that's enough talk. Let's do an example, and we'll see what it looks like. Okay, in my brief example, we've got a simple random sample of voters in the South and another simple random sample of voters in the North, and I'm just looking about how their political party breaks down. So here's the data that I collect in my simple random samples. These are my observations. We're going to have the North, capital N. We're going to have the South, capital S. We have Republicans, R, Democrats, D, and other. Obviously, there's lots of other political parties one can belong to. I'm going to create the matrix using brackets. And here's how my simple random samples broke down. In the North, I found I had 10 Republicans, 32 Democrats, and 8 others. Looks like in the North there was more of a favor on Democrats than Republicans. In my Southern sample, I had 18 Republicans, 14 Democrats, also 8 that fell as other. In the South, it looks like it's a closer match, but Republicans had a higher proportion than Democrats. I always want to find the totals, so I had a total of 28 Republicans, I had a total of 46 Democrats, and 16 that were other. For the North, I counted a total of 50 people, and in the South, I counted a total of 40 people, for a total of 90 in my survey. So far, so good. Okay, while we're here, let's just state our null. What's our null? Well, again, we're doing a test of homogeneity. We know this because there are 2 distinct samples from 2 distinct populations. So my null is going to be that the distributions of political preference are roughly the same between North and South. So we could say political distribution are the same between North and South. And the alternate could be that the political distributions are not the same. Okay? And you could be more specific if you want. That works for me. Let's say we tested a typical alpha of 5%. And I need to check my conditions. Especially because I see I only had 8 that fell as other in both regions. You know that expected counts have to be at least 5. And while 8 is more than 5, it's small enough that it gives us cause for concern without double checking. So I have to verify my conditions. First thing, are both samples SRSs? Well, if you'll rewind to the part where I talked about it, you'll hear me say a simple random sample of the North and also another simple random sample of the South. So yes, that was given to us. The 10% rule. Well, I have 2 samples, 50 in the North, 40 in the South. So long as the population of the North is at least 500 and the population of the South is at least 400, we can continue. Obviously, I said we're talking about voters. Well, there's millions, so yes, we are good to go on that condition. The last condition is for the expected counts. Having at least 5, well, I got to check both samples. Well, really, I have to make my expected value matrix. I can't do anything until I have the expected value matrix. So how do I find the expected value of a cell? Well, again, I'm going to show one calculation, and then I'm going to use the ellipsis, the ... to indicate that we keep doing it without showing all the math on the paper. To find expected counts, it is row total times column total divided by table total. So for each cell reference, we have to look at its row and its column to find that cross-reference. For the first cell, first row, first column, it's going to be 50 times 28 divided by 90. Now, when you multiply 50 and 28 and you divide by 90, you get 15.5 repeating. And the ellipsis, we're going to keep doing that for all of those cell references. I'm going to write down my expected value matrix right here. Okay, again, we have North and we have South. So it was 15.5 repeating. Now, if you want to do this out, you certainly can. Yes, there's a shortcut. I'll show you later. But if you just keep calculating, this would be 25.5 repeating, 8.8 repeating. The south is 12.4 repeating, 20.4 repeating, and 7.1 repeating. Okay. Fortunately, all of those expected values are at least 5. In fact, they're at least 7.1, so our conditions check out. All good? All right, now to find the chi-square matrix, you need to use the chi-square formula of observed minus expected squared divided by expected for each one of those cell references. So 10 minus 15.55555 squared divided by 15.55555. And that's going to get you the chi-square matrix. All right, well, let me write over here how I would do that. So I'm going to show, just like for the expected counts, I showed one calculation. I'm going to do the same thing for my chi-square count. So the chi-square for the first cell, row 1, column 1, is 10 minus 15.5 repeating squared, then divide by 15.5 repeating. That value is 1.9841. ... Wait, I have room for my dots. So let me make the chi-square matrix for the north and the south. And I find we got 1.9841, we got 1.6251, 0.0889. The south is 2.4802, 2.0314, and then 0.1111. Okay, there's my chi-square matrix. Now, does this provide us evidence that lets us reject the null, that the distributions are roughly the same? Or does this provide significant evidence that lets us say that they're different? Might have just said the same thing. Now, how do I move forward? I have to find my chi-square total. So you got to add these 6 numbers together. Chi-square total for this distribution is 8.3208. That's my chi-square total. 8.3208. My degrees of freedom, I said it's rows minus 1 times columns minus 1. Well, there are 2 rows and there's 3 columns, so that gives me 2 degrees of freedom. Want to see a little shortcut to figure out your degrees of freedom? You see your matrix over here? Make an L with your left hand and cover the first column and the first row. I only see 2 values left over. There's only 2 degrees of freedom. Okay, 8.3208 is my chi-square total, 2 degrees of freedom. Use chi-square CDF from 8.3208 to an infinite bound with 2 degrees of freedom. We find a p-value of 0.0156. Okay, I have no more room to write. So 0.0156, I gave you an alpha of 5%. 0.0156 is lower than 5% alpha. That gives me evidence that lets me reject the null. In fact, these distributions are not the same. And specifically, the follow-up analysis is the chi-square values that were the greatest, the highest, they tell you where the greatest difference is. So, I mean, it was pretty off all around the board, except for the others. They were almost exactly what you'd expect. But in the South, the distribution or the proportions of Republicans and Democrats were far different than the North region and pretty much anything else. So what we had here is that there's definitely a difference between the North and the South distribution of political party preference. Okay. Tomorrow I'll show you the calculated shortcut for everything, and we won't worry about additional new information. However, there's a worksheet posted on the Google Classroom to practice the skill. Again, it's optional, but I'd like it if you could do it. It'll give you bonus credit and help you understand the concept. Have a wonderful day.